What if I told you that right now, in this very moment, there's another version of you making the opposite choice you're about to make? Not in some philosophical sense, but as a real physical consequence of quantum mechanics. That's the claim of the multiverse theory, and it's one of the strangest ideas to ever emerge from physics. Let me start with something simple. When you flip a coin, you get heads or tails. But at the quantum level, before you measure it, that coin exists in what we call a superposition. It's both heads and tails at the same time. Now, most physicists say that when you look at the coin, the superposition collapses and you get one result. But in 1957, a graduate student named Hugh Everett proposed something radical. What if it doesn't collapse? What if both outcomes happen, but in different universes? This is the many worlds interpretation of quantum mechanics. Every time a quantum event occurs, and these are happening constantly, trillions of times per second in every atom of your body, the universe splits. In one branch, the electron goes left. In another branch, it goes right. Both universes are equally real, but they can't interact with each other anymore. They've branched off into separate realities. Now, I need to be clear here. This is not proven science. This is one interpretation of quantum mechanics, and there are others. But what makes the many worlds interpretation interesting is that it takes the mathematics of quantum mechanics completely seriously, without adding anything extra. No collapse, no special role for observers, just the equations, playing out to their logical conclusion. Hugh Everett's idea was largely ignored when he first proposed it. He was so discouraged that he left physics entirely and went to work on military operations research. But decades later, physicists started taking it seriously because it solved certain puzzles in quantum mechanics. It explains why we only see one outcome when we measure something, even though the mathematics describes multiple possibilities. We see one outcome because we're in one branch of the universe. The other outcomes are happening, but in branches we can't access. The story of Hugh Everett is actually quite sad. He presented his thesis to Niels Bohr, the grand old man of quantum mechanics, hoping for approval. Bohr essentially dismissed it. The physics establishment wasn't ready for such a radical idea. Everett left academia, worked at the Pentagon doing operations research, and lived a conventional suburban life. But he never stopped thinking about many worlds. He died in 1982, just as his ideas were starting to gain traction. He never got to see the renaissance of interest in his theory. But the many worlds interpretation is just one type of multiverse. There are actually several different multiverse theories, and they're based on different physics. Let me tell you about cosmic inflation. In the 1,980 seconds, physicist Alan Guth proposed that in the first fraction of a second after the Big Bang, the universe expanded faster than the speed of light. This is called inflation, and it solves several problems in cosmology. But here's the thing about inflation. Once it starts, it's very hard to stop everywhere at once. Think of it like boiling water. You don't get one big bubble. You get many bubbles forming in different places. In eternal inflation theory, our Big Bang was just one bubble stopping. But inflation continues forever in other regions, creating endless pocket universes. Each pocket universe could have different physical constants, different laws of physics. In some universes, electrons might be heavier. In others, gravity might be stronger. These aren't separate branches of quantum mechanics. These are completely separate regions of space, so far away that light will never reach us from them. To understand inflation better, let me give you some numbers. During the inflationary period, which lasted maybe 10 to the minus 32 seconds, the universe expanded by a factor of at least 10 to the 26. That means something the size of a proton grew to the size of a golf ball, and then kept going to astronomical scales. This expansion was so fast, so violent, that it smoothed out any irregularities and left the universe remarkably uniform. But quantum mechanics says there will always be tiny fluctuations, even in this smooth background. These quantum fluctuations got stretched to cosmic scales during inflation. And here's the remarkable thing, we can see them. We see them as tiny temperature variations in the cosmic microwave background, the leftover radiation from the Big Bang. These variations are about 1 part in 100,000. And from these tiny seeds, galaxies eventually form. Now, I have to tell you, this makes some physicists very uncomfortable. How do you test a theory about universes you can never see or visit? That's a legitimate question. But the math of inflation does seem to predict this eternal inflation, just like the math of quantum mechanics can be interpreted to predict many worlds. Then there's string theory. We'll talk more about string theory in another episode, but the basic idea is that fundamental particles aren't points, they're tiny vibrating strings. And for the mathematics to work, these strings need extra dimensions beyond the 3 spatial dimensions we experience. The problem is, there are many ways to curl up these extra dimensions. How many ways? Physicists have calculated there could be around 10 to the power of 500 different configurations. That's a 1 followed by 500 zeros. Each configuration would give you a different universe with different physics. This is called the string theory landscape. And again, I need to emphasize this is highly speculative. String theory itself isn't proven, and the landscape is one possible consequence of string theory if it's correct. But it's another way that physics seems to naturally lead to the idea of multiple universes. There's even a more radical idea from physicist Max Tegmark. He proposed what he calls the mathematical universe hypothesis. His argument is simple but mind-bending. Physics describes the universe using mathematics. But what if the universe isn't just described by mathematics? What if it is mathematics? And if our universe is one mathematical structure, why shouldn't every possible mathematical structure exist as a universe? This would be the ultimate multiverse, not just different quantum branches or different physical constants, but different logical structures entirely. Tegmark actually proposes a hierarchy of multiverses. Level 1 is just distant regions beyond our cosmic horizon. These are parts of our universe we can't see because light hasn't had time to reach us. Level 2 is the eternal inflation multiverse, different bubble universes with different laws. Level 3 is the many worlds quantum multiverse. And level 4 is the mathematical multiverse. Every possible mathematical structure exists. Now, you might be asking, why should we take any of this seriously? Here's where the anthropic principle comes in. The laws of physics in our universe seem remarkably fine-tuned for life. If you change certain constants by even a tiny amount, stars couldn't form, or chemistry couldn't exist, or the universe would have collapsed immediately after the Big Bang. For instance, if the strong nuclear force were just 2% stronger, protons would stick together so tightly that hydrogen would be rare, and complex chemistry wouldn't happen. If it were 2% weaker, you couldn't build nuclei heavier than hydrogen, so no carbon, no oxygen, no life. If the cosmological constant were much larger, the universe would have expanded so fast that galaxies could never form. If it were negative and large, the universe would have collapsed in on itself almost immediately. For a long time, this fine-tuning puzzled physicists. It seemed too convenient. But if there's a multiverse with every possible combination of physical constants, then of course we find ourselves in one of the universes where life is possible. We couldn't exist in the others to ask the question. It's like asking why you won the lottery. Well, somebody had to win, and it happened to be you. If there are enough universes, one of them will have the right conditions for us. But here's where I need to channel Feynman's skepticism. Richard Feynman, the physicist this series is inspired by, was brilliant but also deeply practical. He would ask, can you test this? Can you make a prediction that could be proven wrong? That's what separates science from philosophy. The honest answer is that most multiverse theories are very hard to test. By definition, if other universes are separate from ours, we can't directly observe them. Some physicists argue that this makes multiverse theories unscientific. Others argue that if a theory makes testable predictions in our universe and naturally leads to a multiverse as a consequence, then we should take the multiverse seriously, even if we can't directly observe it. For example, eternal inflation makes predictions about patterns in the cosmic microwave background radiation, the leftover light from the Big Bang. We can test those predictions. If the theory passes those tests, then eternal inflation gains credibility, and the multiverse comes along with it. Similarly, if we found evidence for supersymmetry or extra dimensions that would support string theory, and the landscape multiverse would come with the package. There's also the possibility of finding direct evidence. If two bubble universes collided in the distant past, they might have left a circular pattern in the cosmic microwave background. We're looking for that. So far, we haven't found it, but that doesn't mean it's not there. The absence of evidence isn't evidence of absence, especially when you're looking for something subtle. Let me paint you a picture of what the multiverse might mean. If the many worlds interpretation is correct, then every decision you've ever made has spawned countless branches. There are universes where you took that job, and universes where you didn't. Universes where you said yes, and universes where you said no. Every possible history that's consistent with quantum mechanics is playing out somewhere. If eternal inflation is correct, then beyond our cosmic horizon, there are bubbles where the laws of physics are different. Maybe in some of them, there's antimatter instead of matter. Maybe some have different numbers of dimensions we can move through. Maybe some don't have gravity as we know it. Maybe in some universes, the electromagnetic force is much stronger, so atoms are tiny and chemistry works completely differently. And if the string theory landscape is real, then scattered across this infinite space are universes with every possible combination of particle masses and force strengths. Most of them would be sterile, no stars, no planets, no life, but a tiny fraction, like ours, would have just the right conditions. We exist in one of the Goldilocks universes, not too hot, not too cold, just right for complexity and life. This is where the multiverse gets philosophically interesting. For centuries, scientists have tried to figure out why the laws of physics are what they are. Why is the speed of light exactly 299,792,458 meters per second? Why is the electron exactly 1,836 times lighter than the proton? We've always hoped there might be some deep principle that determines these numbers uniquely. But the multiverse offers a different answer. Maybe there is no deep principle. Maybe these numbers are different in different universes, and we just happen to be in one where they allow for complexity and life. That's a less satisfying answer in some ways, but it might be the truth. Nature doesn't owe us satisfying answers. Now, I want to be balanced here. Many respected physicists think the multiverse is bad science. They argue that if you can't test it, you shouldn't believe it. They worry that invoking infinite universes is giving up on finding a deeper explanation. Some even say it's lazy. Instead of solving the problem of fine-tuning, we're just saying, well, there must be other universes where it's different. Paul Steinhardt, one of the pioneers of inflation, has become a critic of eternal inflation for precisely this reason. He argues that it makes the theory unfalsifiable. If any observation can be explained by saying it happened in this bubble and not that bubble, then you haven't really explained anything. You've just pushed the mystery back a level. But other equally respected physicists take it seriously. They point out that the multiverse emerges naturally from theories that do make testable predictions. They argue that if the math leads you there, you should follow the math, even if it's uncomfortable. Science has a history of accepting uncomfortable truths. The Earth isn't the center of the universe. Humans evolved from apes. Time and space are relative. Maybe the multiverse is the next uncomfortable truth. Feynman himself would probably have been skeptical. He was famous for saying, "I think I can safely say that nobody understands quantum mechanics." He preferred to shut up and calculate, to use the equations without worrying too much about interpretation. But he also respected following the mathematics wherever it leads. And the mathematics of quantum mechanics and inflation do seem to point toward multiple universes, whether we like it or not. Here's what I find fascinating about the multiverse debate. It's not just about physics. It's about what we mean by science itself. For 400 years, science has been based on observation and experiment. But now we're confronting theories that make claims about things we can never observe directly. Does that mean they're not science? Or do we need to expand our definition of what counts as scientific evidence? This is actually a deep epistemological question. We believe in atoms, even though for most of history we couldn't see them directly. We believe in black holes, even though by definition we can't see inside them. We believe in the far side of the moon, even when we can't observe it. In each case, we infer the existence of something from its effects. Maybe the multiverse is similar. We can't see it directly, but we can infer it from the structure of our best theories. There's also the quantum computer angle. Quantum computers work by putting qubits into superposition and letting them process multiple possibilities simultaneously. Some researchers, like David Deutsch, argue that this is indirect evidence for many worlds. The computer is actually farming out calculations to parallel universes. Other researchers say that's overinterpreting the math. The computation is happening in Hilbert space, not in physical parallel worlds. The debate continues. Now, let me tell you something interesting about quantum decoherence, because it's crucial for understanding many worlds. When a quantum system interacts with its environment, and everything interacts with its environment, information leaks out. Photons scatter off, air molecules bump into things, thermoradiation goes everywhere. This environmental interaction causes different branches to become effectively independent. They can't interfere with each other anymore. They decohere. Think of it like this. Imagine you've got two pebbles dropped in a pond, making ripples. Initially, those ripples can interfere, make patterns. But if the pond is choppy, waves everywhere, wind, boats passing those specific ripples from your pebbles get lost in the noise. They're still there, but you can't see their interference pattern anymore. That's decoherence. In many worlds, the other branches are still there, still real, but they've decohered from our branch. There's no way to detect them, no way to communicate with them. For all practical purposes, they might as well be in separate universes, which is why people started calling it many worlds. Let me bring this back to something concrete. Whether or not the multiverse exists, thinking about it has forced physicists to clarify their ideas about quantum mechanics, about fine-tuning, about what makes a theory scientific. That's valuable even if the multiverse itself turns out to be wrong. Good ideas don't have to be true to be useful in pushing science forward. And there's something almost poetic about the multiverse. For all of human history, we've been discovering that we're less special than we thought. First, the Earth wasn't the center of the universe. Then the sun wasn't the center of the galaxy. Then our galaxy wasn't the center of anything. It's one of hundreds of billions. Now we're contemplating the possibility that our entire universe, with all its hundreds of billions of galaxies, might be just one bubble in an infinite foam of universes. Some people find that depressing. I find it exhilarating. Even if we're not unique, we're here, we're conscious, and we're able to figure these things out. That's remarkable, regardless of how many universes there are. The fact that we can even conceive of the multiverse, that we can work out its mathematical consequences, that we can ask whether it's real, it's extraordinary. So where does this leave us? The multiverse is not proven. It may not even be provable in the traditional sense. But it's a serious idea that emerges from taking our best theory seriously. Whether it's real or not, we don't know yet. Maybe we'll never know. But the fact that the mathematics of quantum mechanics and cosmology lead so naturally to infinite other worlds suggests that reality might be far stranger and more vast than we ever imagined. And that's the beauty of physics. Just when you think you understand how the universe works, it shows you something deeper, something weirder, something that challenges everything you thought you knew. The multiverse might be real, or it might be a mathematical artifact that doesn't correspond to physical reality. But either way, asking the question has taught us something profound about the nature of existence itself. And that's what science is really about, not just finding answers, but learning to ask better questions. and perhaps discovering that the universe or multiverse is far more magnificent than we ever dared to imagine.